Hi, so I'm going to be talking about peer predictions with heterogeneous users, and this is a joint work with Arpit, Agarwal, Dewitt, and Nisarg, and I think everyone is here. Since Young has done such a good job in explaining the basics of peer prediction, I'll just start with a motivating example about why heterogeneity of users is important in peer prediction. So let's consider this Galaxy Zoo, which is a crowdsourcing project and which asks user to label images whether a particular image contains a supernova or not. So the users can label the images as one of the three categories, whether it's a likely a supernova giving a score of +3, possibly a supernova +1, or it's not a supernova. And so what the prior literature observed, Simpson et al. Observed that there is essentially a heterogeneity among the users. So for example, this is, if you look at this plot, so this is the true class. 0 means that the image does not contain a supernova. 1 is it has a supernova and a score. And some users are accurate, some are extremists. They either give a score of -1 or 3. Some users are non-committal. They do not want to commit to a particular class. So we see that whenever we have this kind of image labeling applications, there is inherent heterogeneity among users. And it's prevalent in other applications. For example, if you want to market, if you go to marketing domains, or even in peer grading, some students do not assign high grades to other students. Some are very flexible, even rating restaurants. And so for all these kinds of setting, we want to design a peer prediction mechanism. And so let me start with some very basic mechanism. So what I will be using this notation is to score reports of two users, where R1 is the report of user 1 and R2 is the report of user 2. So the basic peer prediction mechanism is output agreement, which rewards 1 if the reports of both the users agree. And this has a problem of uninformative equilibria, because if everyone reports the same signal, then that gives a score of 1. And we don't get to know what's the underlying signal observed by the particular user. And there are several ways to fix it. The path we are taking is through multitask mechanisms, and which is particularly useful for image labeling kind of applications where a user completes several tasks. So let me explain briefly what is a multitask mechanism. So there are 3 tasks, let's say T, T prime, and T double prime, and user P completes at least these 2 tasks, and Q completes these 2 tasks. And there is a shared task among user P and Q. And to compute the reward for task T, we use this scoring function, which essentially says that we reward agreement on task T, and we penalize any agreement on the tasks that are not shared. So if now everyone reports the same signal, then this gives a score of 0, because this is also 1, this is 1. So it basically can eliminate those uninformed equilibria. And so let me just briefly, because we will be focusing on informed truthful mechanisms, and just briefly explain what informed truthful means. And it means that the expected payment of user P when both of the agents play truthful strategy is at least the expected payment where the agents play any other strategy profile. And if any uninformed strategy, it's strictly higher. The truthful payment is strictly higher. That means if we have some cost in investing effort, that can be covered by the gaps. Okay, so but the previous mechanisms works for binary signals, and our goal is to work with heterogeneous agents and multiple signals. And Snyder et al. Generalized the multitask mechanism for multiple signals. The idea is the following. So we compute the delta matrix, which is the difference between joint probability and product of marginals, which is in some sense captures the correlation among the signals, and then use the sign of the delta matrix as the score function. And so throughout this talk we'll use different delta matrices. So I just want to highlight that this is a very key part of our talk. And yeah, with this generalization, CA mechanism can again eliminate any uninformed equilibria. And so if you go to heterogeneous agents, a natural generalization would be just learn the delta PQ for every pair of agents P and Q, and then use that sign of the corresponding delta matrix when agent P is paired with user Q. Okay, so the problem is that if we have now L users, we need to learn the delta matrix for each pair of users. And when we are trying to apply these mechanisms in practice, we actually get labels from the users, and from those labels we try to estimate the delta matrices, and which says that the number of reports will grow with the number of quadratically with the number of users. And so we ask, can we do better? And without any assumption we cannot do anything. And so what we saw earlier, that there exists essentially some clustering or communities among the crowds, and so we assume that the agents can be clustered into a constant number of groups, and if the number of groups is small, we want to improve upon the number of reports needed to run these kinds of mechanisms. So, but this also introduces some trade-off. So for example, this was the unclustered setting, and where we need to learn L square matrices, and if we cluster the agents into K groups, we need to learn now K squared delta matrices. But when I pick one user from this group and one user from here, I am, instead of using a true delta matrix, I will be using a pairwise delta matrix, and that introduces some error in the clustering. And that error is introduced by how well we can cluster the agents, and that's sort of inherent in the mechanism, and we cannot overcome it through learning or anything else. Okay, so now I'll just give a brief overview of our results. So we designed a multitask mechanism for heterogeneous users, and the specific setting we have in mind is that the users can be clustered. We derive sample complexity bounds for this setting, and we will also see that there is a connection between pair prediction and how to learn the latent labels, and Davidskin is the sort of standard literature for this setting, and there are several sample complexity results for learning the ground truth, and we will see a connection between them. And we will also present some experimental results to see that in real world setting the users can actually be clustered. Okay, so yeah, as I said before, so if we were to run the naive mechanism, we need to learn the delta matrix for each pair of users. So instead now we will learn one delta matrix for the two clusters G1 and G2. And so our goal is, but this is sort of the ideal delta matrix, and we can't learn it exactly, but we get reports from the users and form an estimate of the delta matrix. So the first step is to learn to replace the individual delta matrix with a cluster-wise delta matrix, and that has an error of epsilon1. And the second step is to replace the pairwise delta matrix between two clusters by an estimate of the pairwise delta matrix for the clusters. And let's suppose that error is corresponding epsilon2, and the mechanism we run is for two users P and Q. GP denotes the cluster of user P, and GQ denotes the cluster of GQ. And we use the scoring matrix, the estimate of the delta matrix for that pair of clusters. And it can be shown that the error is sort of additive. It gives epsilon 1 plus epsilon 2 informed truthful mechanism. Yep. So we call this mechanism CAHU, correlated agreement for heterogeneous users. And yes, so now I will briefly sort of overview the sample complexity results and for this setting. So we have k clusters, and we need to learn the pairwise delta matrices for the clusters. And we have two questions related to sample complexity. One is, how do we cluster the agents? So for example, if I pick two users P and Q, our mechanism needs to know the cluster of user P and Q, how many reports we need. And the second is, once we have determined the cluster identity of the agents, we need to determine the corresponding delta matrices and how many samples we need to estimate that thing. And finally, is it a reasonable assumption? Okay, so I will not go into the details of clustering, but you can cluster the agents by sort of linear, that with a sample that grows linearly with the number of agents L, because you have to sort of cluster each agent, so it's intuitive that it has to be linear, and grows with quadratically with number of signals n, and for all practical reasons n is sort of, you can think of as a constant. And gamma is sort of cluster parameter that captures how close the different clusters are. Okay, so now to determine to estimate the pairwise cluster matrices, we can do it either without assuming that there is a ground truth, or assuming there is a ground truth. So I will just focus here for the case where there is a ground truth. And the standard literature is the Davidskin model, which says that each agent P can be characterized by a confusion matrix CP, and the corresponding ijth entry of this matrix gives the probability that user P confuses a true signal I to be signal J. And so let's assume that pi k is the prior probability of signal k. So if we know the confusion matrices of two users CP and CQ and the prior probabilities, we can write down the joint probability of observing a pair of signals I and J. So which is the sum of, the first term is the probability of signal k, and user P confuses k to be I and Q confuses k to J. And once we can write down the pairwise joint probabilities, we can compute the delta matrices, because this is just the difference between joint probabilities and the product of marginals. So, but in practice we do not get to see the confusion matrix exactly, but we will form an estimate of the confusion matrix and what's the corresponding error in the delta matrix. So if we can estimate in one norm the confusion matrix is close to the true matrix, we can also show that the corresponding delta matrix in one norm will be close to the true delta matrix. Okay, so now in order to estimate the pairwise pairwise delta matrices, our goal is to sort of estimate the confusion matrices from each cluster. So by confusion matrix from each cluster, I mean I just compute the average confusion matrix from each cluster, and since once we have computed the average confusion matrix, we can use those confusion matrices to form the estimate. Okay, so so the basic idea we'll use is the tensor decomposition method. So let's fix a particular group S, and the aggregate level for group S, so this shows the aggregate levels, so which means that, let's say this is signal 1, 0.5 is the empirical frequency of signal 1, and this is for signal n. And we can write down as this formula, so this is CS is the aggregate confusion matrix for cluster S, and K is the corresponding kth row. 5 minutes, okay. And so once we write down this, then the steps are you write down the higher moments and try to back out these C's. And the tensor decomposition method originally works with, so we are given a particular realizations of a fixed tensor, and we want to back out the particular tensor, but here we can do slightly better because we don't need to estimate the individual confusion matrix, but we need to estimate only the aggregate confusion matrix. So we can improve upon the standard sample complexity results. Okay, so so here I will just briefly give an overview of the sample complexity results that we get. So if we do not make any assumptions, it roughly grows with L squared n squared, where L is the number of users and n is the number of samples. And if we assume that there are k clusters, then the first part becomes ln squared, which is for the clustering, and the second part is k squared n squared, which is to estimate k squared delta matrices. And further, if we assume a ground truth model in the sense of Davidskin, then the k square can be improved to k. Sorry. Yeah, this becomes n power 7, but you can think of n as being very small. Okay, so the final thing I want to talk about is the clusterability a reasonable assumption? And to test that, what we do is we take several real-world crowdsourcing datasets where we have ground truth, and the users provide noisy levels for several tasks, and from those levels we can compute the empirical frequencies for a particular signal, and that gives us the confusion matrix for each user. And once we compute the confusion matrix, we can cluster the agents by k-means algorithm. And so what we will study is if we increase the number of clusters, how the incentive bound changes. So the x-axis here shows the k, which is the percentage of number of workers. So for all of these datasets, the number of workers were around, I think, 400 to 500. And to understand the incentive bound, the maximum an agent can get paid in our mechanism is 1. And if we see that the number of the percentage k as a percentage of worker, if it goes beyond, let's say, 15%, then it becomes roughly around 0.1 incentives, and this gives the bound in our approximate informed truthful mechanisms. Okay, so to conclude, we provide a solution to peer prediction with heterogeneous users, mainly by computing sample complexity of both clustering and learning. And we also saw some connection between peer prediction and learning latent models of level aggregation. And there are several directions for future work. For example, what happens if the tasks are also inherently heterogeneous? We can have complex signal structures. For example, users are reporting ranks, and we only considered binary effort model, and suppose we can incentivize the users to provide multiple effort levels, and that can give us better signals. That's it.